Hi, everybody. Can you hear me okay?
Yes, thank
Thanks.
you.
Great. So it's 3 a.m. here on the West Coast. I'm going to do the best I can, but cut me some slack. And I'm going to kind of pile on some of these questions about WebAssembly and what the potential use cases of it are. And hopefully I can't answer the question, but hopefully I can add a little bit to the discussion. So I'm mostly going to be talking today about a library I've created called genish.js. It's a JavaScript port of the gen extension to MaxMSP jitter. And it's a graph-based system for single sample processing, low-level nodes to do things like read and write from buffers, single sample feedback. And I use this in a couple of other libraries that are built on top of it. And in particular, I wanted to point out one of them, which is this library for Gibber and doing live coding, because having dynamic graphs that are constantly in flux is a big part of what this research is and might differentiate it from some of the other conversations that we've been having so far in this session. So currently the way Genish works, or in the original version, is you define an audio graph using a JavaScript API. Genish then compiles that graph into a flattened JavaScript function. So you have one JavaScript function that represents the entire graph. At runtime, the JIT compiler optimizes this, and then the JIT optimized function is used to generate audio in an audio worklet processor. And so this has a couple of advantages. The end function can be pretty fast. And so yeah, in a 2017 paper I presented at WAC, I had results that were on par in certain situations with the native nodes. In other situations, the native nodes blew it away. But in some cases, it can be really, really fast. And being able to support single sample feedback is really important for DSP and sample accurate scheduling as well. So those are some of the things that Genish had going for it that were great. Disadvantage is the graph is static. So I'm compiling everything into a single JavaScript function. And that means if I want to change the graph, I have to recompile that function, and then the JIT has to re-optimize the function. And in particular, the JIT optimization is something that can lead to audio dropouts if you're using a low buffer size for your audio callbacks. The other problem that's already been mentioned by Gerard and others is this garbage collection when you're using JS. Genish has a single static memory heap that it uses for all of its DSP memory, but there's still only so much you can do to avoid garbage collection, which is something else that can potentially cause audio dropouts. So for these two reasons, wanting to be able to have more dynamic graphs and also wanting to avoid garbage collection, I wanted to move Genish to WebAssembly. So with WebAssembly, you get ahead of time compilation, which means you don't have to wait for the JIT to optimize at all. This might not be an issue if you're only loading your JavaScript function once and it's then running for the duration of your time on the browser page, and you're never having to modify it or optimize it again. But if you're having an audio graph that's constantly changing, then it becomes a problem, the JIT optimization. And then also to get rid of the garbage collection. Notice I did not put computational efficiency in this list. And so that was kind of an open question when I started this, and we'll talk a little bit more about that in a second. So how? The way I did this is a little bit different from what's been talked about so far. I decided to port Genish directly to WebAssembly or the WebAssembly text format. So Gerard mentioned that there's this text format that can be freely converted back and forth to the binary WASM representation. And it's not that scary when you look at it. This is the actual WAP file for Genish. This is a function to, maybe that one's a little harder to explain, but this is a function to round up a number. It loads it out of memory after looking up the memory location, and then it just calls this function on it to go ahead and round it up. And for me, I thought it was interesting to actually learn WebAssembly at that low level just out of curiosity, and potentially I had an idea that maybe there were additional optimizations that I could do if I really understood the language at a lower level. So those are some of the motivations for kind of writing it directly in WebAssembly, as opposed to using a compiler from Rust or C++ or AssemblyScript or any of these other languages. But of course, I'm giving up all the amazing abstractions that these languages provide to make it easier to code. So I'm not trying to diminish the trade-offs here, but those are some of the justifications I had for choosing to go with WebAssembly text. So this version 2 of Genish kind of works like this. You still define your audio graph using a JS API. The JS API then creates a memory layout in a shared array buffer, which is shared with the WASM kernel. That runs bytecode using that allocated shared memory. And then the audio workload processor node uses samples generated by the WASM kernel. So the one big difference is that this bytecode is completely dynamic in the version that I'm talking about right now. So you can easily just go and change a location in memory to completely alter the function that's processing a particular chunk of memory and enable all sorts of different types of shenanigans. So I'm going to do a couple of demos right now, just looking at some of to kind of illustrate the differences between the original JavaScript version of Genish and this new version in terms of performance and what some of the problems were that I stumbled upon. So this is the original Genish playground, and it has a whole bunch of tutorials and different examples of DSP algorithms if people are interested in checking it out. But I'm just going to jump down to the bottom of this introductory one and look at the raw oscillator tutorial. I'm going to change the number of oscillators to 150 here and go ahead and run this. I don't know if you can hear that annoying buzzing sound or not. It's not super important if you can't, but hopefully you can see in the bottom corner the render capacity, which is about, we're hovering around between 5.5% and 6% for 150 sine oscillators, which is pretty great. And you can see here that there is this one big, long JavaScript function that has been compiled. So this is the flattened audio graph reduced to a single function. The JIT optimizer can handle that, and you get this great performance out of it, or I think it's pretty good performance. But let me just refresh this to make sure it runs again. If I take this same code and let's do 350 oscillators. So down at the bottom here, hopefully you can see it. Let me bring it up just to make sure it's in the video feed. It's at 99% and it's not moving. So this is basically a point where the function that I've compiled is just so large, so many lines of code, so many expressions inside of it, that the JIT optimizer can't do anything with it. So even though you would think this would 350 oscillators, well, it's a little more than double 150. So we should have, 12 to 15%. That would be our render capacity. It actually just doesn't even work because the JIT optimizer just kind of gives up, and you can't run this function fast enough to get real-time audio happening inside of there. So I have this other dynamic WASM version, and there's a lot of technical details about how I implemented the dynamic WASM version in the paper that I'm not going to get into here. But there's also a playground that's linked in the paper where a lot of the same examples and tutorials are present, but using this dynamic WASM version. So I'm going to do kind of the same thing. I'm going to go down here and we can start with 150 just to get a sense of how that compared to the JavaScript example. Why is it doing that? It's doing that because I left open the other tab that still has 99% of the core running. Let's copy this, refresh this. Let me try that again. So it's coming in at 26. That's actually higher than I feel like I usually see it. But that's 4 times as much. I feel like in the past, I'm just gonna run one more time just to make sure I'm not crazy. Yeah, it's giving some variable performance. Earlier when I was testing it, it was getting even lower than that, but it was still at least twice, even in the best tests that I've had running it, the values that I was seeing there with the JavaScript version. But I can go here and I can say, oh, I want 850 of these oscillators, or here's 800. And it runs. It's able to do 800, somewhere between 80 and 90% of the CPU. I don't know if you can hear the sound, but it's changing. It's not, there's no dropouts that are happening with it. Or if there are, it's probably because of Zoom and OBS running and everything else that I'm doing as well. So it doesn't crap out like the JIT optimizer did trying to do this. So that's another potential advantage that the WASM version of this had that the JavaScript version didn't. So some offline rendering numbers. When I did this with an offline audio context, 100 sine oscillators rendered for a minute over 50 runs. You can see the results right here. The WASM version is a little more than 2 times slower than the JavaScript version. And when I ran these tests, I was like, okay, this is good enough for me. That's fine. I'm willing to live with that because now I am going to get no JIT optimizing, potentially causing dropouts, no garbage collection, potentially causing dropouts, and my graph is going to be completely dynamic. I'm not going to have to recompile it every time I want to change the audio graph. So I started doing some tests with more complex instruments. And when you have really flat graphs or really simple graphs, the performance is really good. But when you have dynamic large graphs, the performance becomes problematic. And I think I can't remember if it was Gerard or Xiang mentioned this, but there's some penalty associated with calling any function dynamically. It's the same when you use a function pointer inside of C. WebAssembly has its own method for calling a function by giving it a pointer. And when everything is dynamic like this, that overhead actually adds up. When you have more complex instruments with hundreds of nodes, think anti-oscillators feeding into a virtual analog filter with envelopes and whatever other features you might want to add to it, it became a little bit too expensive. So then I started investigating, well, if I can't use the dynamic version for these instruments and these more complicated effects, why don't I just have Genish compile large WASM functions similar to how it was previously compiling large JavaScript functions? And doing that, the dynamic version, when I did this test last, and this is not the result we just saw, but when I did this test previously, I got about 1,500 sine oscillators at 85% of a single core. But the compiled version could do 3,000 sine oscillators at about 40% of a single core. So there's clearly a benefit to compiling these large WASM functions, or compiling instruments basically into single WASM functions that can be called in one fell swoop versus having these dynamic graphs that are all linked together. So what are the possible conclusions? I I want to use this low-level kind of dynamic library, and I think it's going to be super useful for my use case, which is primarily live coding performance, also for exploratory DSP experiments and for educational purposes. But the compiling the large graphs to single WASM functions is definitely a lot more efficient. And I should mention also that the WASM library itself is only 10 kilobytes, and the JavaScript board is only another 20 kilobytes. So it's only 30 kilobytes compared to, I think it's close to 500 kilobytes for the original JavaScript Genish version. So it's a really big difference in that as well. But I'm hopeful that being able to compile this dynamic version and being able to live code that with precompiled instruments is kind of going to be a sweet spot to bring these different make the new versions of Gibber and Gibberish possible. And with that, thanks, and I'll take some questions.
Thank you.
Oh, I guess I can't do, let me see, how can I do this? Okay.
Does anyone has a question?
Hi, thanks for the talk. I was wondering, how often do you regenerate the graph in Gibber every time you evaluate, or more often? And you mostly talked about the performance of the graph itself, but I wonder how the performance of the graph generation is and how fast it is, because it's also interesting for me for live coding.
Yeah, so in Gibber, there's actually like two levels of, at least two levels of code generation that happen. But for the DSP side of things, two levels of code generation that happen. So you have like these lower level Genish functions that are used to create instruments. And then there's like a higher level graph that Gibberish handles to link all those different things, those Genish functions together and route to buses and whatnot. So it happens whenever you instantiate a new instrument or add a new effect. Those are basically the times when the code generation takes place. It's mainly during instantiation of instruments, which can happen quite a lot during a live coding performance.
Okay, so but if you do nothing to the code, then nothing will be generated.
If you do nothing to the code, yeah, it'll only be generated once, and then it'll just run without having any changes. Yeah.
Okay.
Jan had a question online.
Yes.
He asked about the 4 times improved performance with the compiled version, and why that is so different. And yeah, I think it's all due to graph overhead. I really do think that's what it is. And I did do some tests just trying to figure out if it was the function call, the dynamic function pointer resolving that was causing it. And it really did seem to be the case.
Thank you.
Hello, thank you for your talk. And I was wondering why you go for the one sample base approach. What are the advantages over the buffer?
There's just, I guess, primarily, there's lots of DSP algorithms that you just have to have the single sample approach. And so FM, for example, you know, the canonical FM algorithms on the original Yamaha instruments, they all had a single sample feedback loop inside of it, you know, things that you can't do with the built-in web audio nodes. And so I definitely wanted those types of things to be available in the library.
Thank you.